powerful. So that's what I want to talk about today. Let's go to the next slide. What's an automatic set? So if I have an integer, I can look at it in base k, whatever k is. Write it down. And I'm going to say a set is k automatic, or k recognizable, a set of integers, if the set of, if the representation, the sets of representations of those numbers, base k, is sigma recognizable. That is, there's a finite automata on this alphabet, so that it's happy precisely when you feed it one of these numbers in base k. So this is a special vocabulary, a special set of language. So this is the definition of automatic sets. I can't resist saying how much I dislike that term. The automatic just refers to automata, doesn't refer to the usual meaning of automatic. So let's look at an automatic set. So I claim the sets of powers of 2 is 2 automatic. I want to ask, is it 3 automatic? Well, here's this automata that I showed before. If you have a power of 2, base 2, it starts with a 1, and then it's a bunch of zeros. You start with a 1, and if all you see is zeros after that, you're going to stay here. If you start, somehow things were screwy, and you started with a 0, well, you get down here, and you're just going to stay there. If you start with a 1, and if you happen to encounter another 1, you'll go to this garbage state, and you'll stay there. So this automaton recognizes precisely the powers of 2 is 2. So that's a 2 automatic set. Well, what about, can I do it if I write the powers of 2 in base 3? And the answer is no. And this is a theorem of Kappa. So let me explain some of the terms here. K and L are integers. Multiplicatively independent is no power, no non-zero power of 1 is a non-zero power of 1. So it's a weaker statement and relatively prime, but it's somehow it. And a subset of integers, if you can recognize the base k representations of that set, and you can recognize the base L representation, then the set is ultimately periodic. And that means that something's in there's, after a certain point, there's an integer b such that something is in the set, then x plus d is in the set. And certainly the powers of 2 don't have this property. It's not some arithmetic sequence. Okay. And this was proved in the 1969. By the time Eilenberg wrote his book, I don't think he included a proof, but he had the following statement. The proof is long and hard, so challenge to find a more reasonable proof. And since then, there have been more reasonable proofs. The one I think that's most intriguing, maybe second most intriguing, is the one due to Michaud and Villemary, which Villemare, sorry, thank you. Spelled it here. So there's a theorem of Bucchi that says if you look at the integers with plus, look at the theory of that, structure, then you can extend that with a new predicate. I'm not going to say what the predicate is, such that a set of integers is, well, you have a new predicate for each k, and a set of integers is k automatic or recognizable if and only if it's definable with this new predicate. And using this theorem of Yuki and a lot of work, they were able to give a proof of this. And the papers, I haven't read it in detail, but it's quite accessible and quite interesting. So this is the result I'd like to talk about. So at this point, I'm going to stop this and talk about difference equations. And my difference equations come up in this context. And here's the reason. So if I start with a k-automatic set, and I look at this generating function. So it's the generating function on sum over powers of x. Power of x appears if and only if that power is in the set. And so if S is automatic, then this generating function will satisfy this k-molar equation. So it's a difference equation with respect to a following automorphism. So, usually we think of difference equations. Say y of x equals 1, or y of x goes to ux. And here I'm saying y of x should go to y of x to the k in intervals. So this is the connection. It's not a difficult theorem to prove, but you end up proving a little more than what you want, and setting up the proof and the notation you take the rest of the calculus. It's not such a bad result. But I do want to explain what this x goes to x to the k has to do with automatic sets. Why is this something that comes up? And
what's the m?
Excuse me?
The m, the arbitrary?
Yeah. So this is an order m difference equation. So what does x go to x to the k have to do with k recognizable sets, k automatic sets? And the way I think of it is the following. So you have some base k representation of a number. So your machine is moving along. It has read this number. If you think of this just as a number, this is A0 k to the t minus 1, k t minus 2, plus 1. That's the number it's looking at. And now it's going to look at A0 t minus 1 t, which is A0 k to the t plus t. So the way you get from this number to this number, do it this way. So if I look at x to the A0 at minus 1 t, this is going to be x to the k times A0 at minus 1 times perhaps x to the at. So if you are coding up your numbers as powers of x, the way the machine would go from here to here is substituting x to the k to x. That's correct.
So the fact that that it's a finite automaton is just going to make a finite equation, or I mean?
Yeah. And so you have to code up the steps, the graph, what it's doing, in terms of this substitution. And when you do that, you get this result. That's all I'm going to say.
So are the coefficients of the AIs, are they in C or they are actually in Z? Or?
So they are, let's say, rational functions, in this case, in Z.
Z, right? I mean, you're not going to.
But I'm interested in these K-Mahler equations in general. Okay, so my powers of 2, 4, you can verify this equation, or tell me that it's wrong. Okay, so there's an interesting result about these K-Mahler equations, Bell. And again, it's a result that says if K and L are multiplicatively independent, and you have a power series that satisfies an equation like this with K, an equation perhaps in a different order with L, then that power series is the expansion of a rational function. Well, gee, I mean, there should be some connection between this and Cobham's theorem. And of course, in the paper of Winchevsky and Bell, they give the connection. So let me restate Cobham's theorem. So always K and L are multiplicatively independent. A set is both K and L automatic, and only if it's ultimately periodic, and a power series satisfies a K and L Mahler equation when it's a rational function. Probably. And Adamczewski and Bell show how this result implies that, and I'd like to give their proof because it's on the slide and it's nice. So I'm going to assume this result, prove that. So first of all, with your automatic set, you form this generating function. And then, if it's K automatic, it's going to satisfy some Mahler equation with respect to K, and L automatic satisfies a Mahler equation with respect to L. And then the theorem says that the power series has to be a rational function. Okay? So we're going to expand this. So if you clear denominators, multiply through, I've written this generating functions. I've put alpha n's here. They're zeros and ones. If you compare powers of x, for large enough I, you're going to get an equation like this. So just think about multiplying out. You multiply this out for some combined terms. This is what the coefficient will be. Once I'm beyond powers of x that appear here, it's 0. And I can assume that A0 is not 0. So I divide. And now what do I have? These alphas are zeros and ones. There are only a finite number of possibilities you can have here. Eventually you have to start repeating yourself. And at that point it becomes clear. So that's the proof that the set is something. And it's a great proof of Cobham's theorem. The only slight problem is that the proof that Adamczewski and Bell gave for their theorem uses copies. So that's you know, it's a very nice proof. I don't mean to mock this. It's something they note and they say. Hide this fact. Their proof is very nice. It involves a lot of commutative algebra.
So
reduce this to questions of
so does that mean the two are equivalent, the two theorems?
Yeah, I mean,
Okay.
I guess any two theorems are equivalent in some sense. But yeah, the proof is nice. It uses eventually reduced to a situation where you're looking at things mod P, and that's where the Cobham's theorem comes in. So nice results of commutative algebra. Our theorem comes into play. It's very nice. So with Shefka and I, we got some results, and after we got these results, we realized that we could give a proof of this Adamczewski theorem that it doesn't depend on copies. So that's this comment. So, as it turns out, there are many results that are similar to the Adamczewski-Bell result. I'd like to talk about some of these. And keep repeating this. So this is the Adamczewski-Bell result. You have something that satisfies two different equations, then it's a rational function. So, a similar result is due to Ramis. You have a power series. It satisfies a linear differential equation and a Q difference equation, and it's also rational. So you have power series satisfies two different equations, and the conclusion is the power series represents a rational function. And there are a large collection of results like this. So we'll start with two equations. The D will be different kinds of operators. Let me start by listing some of these results. So this was the Ramis result. Power series, Laurent series, satisfies an equation with respect to the derivation, satisfies an equation with respect to the Q dilation, then it has to be rational. Another result is with respect to Mahler equations. You have a rational function satisfies the differential equation and the Mahler equation. Again, it's rational. Here, there's a result. I want to think about the shift. Well, if you have a power series, in general, you can't replace x by x plus 1 unless you know something about convergence. But if you have a power series in 1 over x, if you replace x by x plus 1, then it again is a power series in 1 over x. So that makes sense. So here, for power series in 1 over x, the similar result holds.
That's what Ramis theorem. What is the condition on the operator, on the difference operator? None.
On the Q is not a root of 1.
That's the only.
That's it. It can have absolute value 1, but it can't be a root of 1. And it's a complex number. And there are just lots of results. For two Q difference equations, it gets the same kind of result. For the Mahler equations, that's the Bell result. For two shifts, well, this is a result of Shefka and I. I'm sure something like this appears in the literature, but I haven't found it. One can think about meromorphic functions, and these results have been proven by Elizabeth and that. The star means some restrictions apply. Say exactly what they are, but Chef did away with these restrictions. One can classify certain functions that on Riemann surfaces that satisfy these kinds of equations as well. So the point is we have a general approach which gives at least a uniform philosophy for attacking these kinds of problems, but of course in each case one has the details become different. And I'd like to talk about this philosophy. So I'm now going to leave automata behind and just think about difference equations and differential equations. Okay. So I showed you how this result implies Cobham's theorem. I want to state another result of Shefka and myself that implies this result. And it's the following. So I apologize in advance. It's going to fill up the rest of the slide, but we'll stare at it for a while. So the Adamczewski result talks about scalar equations, nth order scalar equations, and this result talks about first order systems. That's the first difference. So I take two first order systems with respect to this Mahler operator, and I'm going to assume they're consistent. I'll tell you what that means in a minute. So that's some condition. And if they satisfy this condition, I can make a so-called gauge transformation. I define a new variable, which is some invertible matrix with rational function entries, such that the new variable satisfies this very simple difference equation. These b's are now constant matrices, whereas these guys were matrices with rational function entries. So there are several differences.
C is what?
Yeah. Yeah, let's say that.
And there is an L missing, or I'm missing an L? Ah, L, I see.
There's
No, B.
yeah, I should class it straight. So this is a result about solutions. This is a result about equations. There's no mention of solutions here. I'm saying if you have a pair of equations that satisfy some condition, then they can be simple. And let me tell you what the consistency condition is. It's not such a surprise.
Sorry.
Yeah.
What is S with respect to K and L? Is the
Excuse me?
What is S with respect to K
Yeah,
and L?
well, I need to go to fractional powers of x. It's not enough just to look at rational functions in x. And S is something.
No, but it's computable. I mean, it says a specific number in terms of L and K. No.
I think it is. I'd have to.
Okay.
There's a good chance that it is. This is kind of a technicality. And so, what is this consistency condition? Well, replacing x by x to the k, or replacing x by x to the L, it doesn't matter what order you do them in. Right? You can do one and then the other one and then the first one. So if I would have a solution of this that was an actual function, then if I take this equation and here replace x by x to the L and put it in here, and compare it with this equation where I replace x by x to the k and put it in here, this is the condition you would have. You have to do the computation. That's the consistency condition. Nonetheless, I'm not talking about solutions. This condition does not mention any solutions. It's just a condition on the matrices. And for better or worse, I have enough time to show you how this implies that. And so I
May I ask? Sorry,
yeah, sure.
So is this consistency that the operators have to commute, is
Yeah.
this going to be the same thing for difference and differential?
Yeah,
Or a similar?
when you say the operators, some restrictions apply, as we say.
Okay.
So I have to tell you what the operators are. So for instance, with the Q difference equation, it's not just the derivation, it's x times dx that I want to commute to, because it does.
Okay.
So the condition is, whatever these operators do on the rational functions, whatever identity holds for these operators on the rational functions, I want it to continue. So that's the way you should think about the consistency conditions.
And you want them also to move in house?
I just want them to hold somewhere. This has nothing to do with solutions. But of course the philosophy is
The g of x actually follows these roots x to the 1 over s.
Mhm. Yeah. Okay.
yeah. So it's in it's an invertible matrix K.
But it really follows that.
It could.
Z also.
Well, now I've lost track of Z. I think here I can't guarantee that it stays. It's pretty. So after telling you so much about how proud I am that this doesn't mention solutions, the proof is analytic, and at some point I need to produce a solution of some difference equation, and then I've lost control of the coefficients. On the other hand, I think working backwards, let me try not to say too many wrong things. So how does this proof work? And I think people who work with difference equations know, or differential equations know, that there's some relationship between linear scalar equations and systems. And I just, the relation is, it's not that relation that comes up. So I'm going to start with, let's call this K bar, which is the field of Puiseux series. Okay. I'm sorry, not series, but Puiseux rational functions. Okay. Excuse me? No. Because I already have a K. No, I have too many notes. Yeah, everybody, every notation I use, somebody else is going to use for some difference.
Okay, put the bar back.
Thank you. So I'm now going to start with this Adamchevsky result, and I'm going to look at a vector space spanned by, well, I'm going to take my function f, and I'm going to look at the following. What did I use for now? L. So I look at this, where I'm in J. So a priori, this is some infinite set. But because I have these Mahler equations, you can see that this space becomes finite dimensional. That is, a high enough power, f of a high enough power of x can be expressed in lower powers. That's what the linear equation tells you. So this is finite dimensional. So let's say the dimension v is n. The dimension is a K-bar space.
Excuse me.
Yeah?
You should have some k to the I, or
Excuse me?
it's not a k to the I.
No.
Okay. I think that's correct now. Or do I like to multiply?
Multiply.
Yeah?
You must have said it that I used the just capital F.
Yeah, the solution.
F is this function.
Oh,
It's a
oh,
power
thank you, thank you,
series.
thank you.
Power series.
Thank you.
Okay. And I'm going to pick a basis. G1, Gn, basis, D. I'm going to, let's say, G bar, be this vector. Now, this is going to be a vector space that is stable under substitution. So if I take G and replace x by x to the k, I'm going to get some matrix times G. And if I replace G by x to the L, I'm going to get some other matrix. And of course, these x's will involve fractional powers. And I'm now going to cheat and pretend that, of course, I've proved the theorem when these entries have fractional powers as well. That's not a serious problem. Yeah, right. It's okay. Not the way I say it. Okay, so now my this second theorem says I can make a change of basis in this vector space. I can choose a matrix with entries in K at bar, so that in the new basis, so there exists g of x is in the theorem, so that I make the change of basis, I get a new equation, two new equations. This. And what I'm doing really is I'm changing the basis of V. Okay? I just have a new basis, H arrow G X H arrow is HM is a new basis. And now, let's look at this. So H arrow is going to satisfy, let's say, the first equation. And now, what is H? H is some sum of let's call it AI x to the I over s for some s. And now AI is a column vector of complex numbers. So I'm using so what's h of x to the k is summation ai x to the k s, and I said it's B1. Well, B1's a constant matrix. So I can pull it in. Sorry, it's standing in the way. And if you think about this for a second and compare powers, you're going to see that all of these are 0 except when I is 0. You just have to equate things. And I get that AI is 0 unless perhaps I is 0. So this this guy, where have I put it? This guy is constant. So my g's are just going to come from this, which is some rational functions in a fractional power. So the conclusion that I want to make is that G is going to be G of x times some constant matrix. So the GI are actually going to be in my K bar. Think about that for a second. That just means that n would have to be 1. And my y of x, my f of x, now is in some c of x to the 1 over s intersect this and that's.
I mean,
First one.
the reason right.
I'm sorry. I'm sorry. Thank you. And that's what I want. So, I mean, the proof was drawn out, but the basic idea is that this thing has very simple solutions. I can write the solutions of this in terms of these solutions. So this would have simple solutions. Yeah?
So, seems to me that you don't use the second max term.
I use the second one to get to here.
Yeah, but
And then here, I just
computation-
use the first one. And in fact, that's true. You don't like that?
No, but well, I was thinking.
Thinking
To
is
unknown,
always
yeah.
dangerous.
Yeah.
So in general, would you look at the vector space generated by all possible
Yeah.
words in the operators? Or if the operators don't happen to commute, they are just...
If they don't happen to commute, you're not going to get to here.
I will ask
Bother me
after.
later.
Yeah.
So, okay. So that's the. So that's how this result applies that result. So now the question is, how does one prove that result? I hope to run out of time at this point. Yeah, let me talk. Let me filibuster a bit. There are similar results for Ramesses' theorem. That is, here's Ramesses' theorem. F satisfies a linear differential equation. difference equation, whether this is a rational function. Q, of course, is never a root of 1. The corresponding result is if you have a linear differential system and a Q difference system, again, there's some consistency result, then you can transform them into a simple system. And the consistency result is that you want this derivation to commute with this. When you write that here, you get this condition. So this is the formal condition. It's not so pleasant to look at, but it's meaning. So how does one prove these results? And the philosophy is the following. When you have this consistency statement, so you have one equation which is either a difference equation or a differential equation, and the other equation is always a difference equation. And to say that they're consistent, it turns out it means that at a singular point, your first equation has some symmetries. That is, the second equation, the fact that they're consistent, will impose symmetries on the first equation. So if you have a singularity with some kind of symmetries, you should be able to simplify it. And systems with simple singularities, in this case, part of the philosophy is, they're equivalent to simple systems. And then to finish, to get the kind of Ramis and other results, simple systems have simple solutions. So it's a simple and since I do have a few more minutes, I do want to give you some idea of what this means. In a certain case, I don't want to do it for the Chevsky-Bell result, but I will do it in the situation of Ramis' theorem. And I want to do it for first order equations. Now, first order equations, you probably could give this to a high school student or somebody and have them work it out, but we'll try and do this using the philosophy. So I'm just going to look at this very simple equation. A of x is just now some rational function, a1 and a2. And I claim that you can make a simple change of variables so that this equation becomes the solution. Let's see. I have my notes. So there are so this Q shift, Qx goes to Qx. If you think about what it does to points on the Riemann sphere, it leaves 0 fixed, and it leaves infinity fixed, but every other point is going to get moved. And since Q is not a root of unity, it'll get moved to an infinite number of points. You're never going to get back at yourself. So, just going to tell you what that means. So, I started with dy dx is a1 of x, y of x. And the consistency condition implies the following, that if I let w be a2 of x, y of x, which is the result of substituting qx into x, the consistency condition, this new guy satisfies dw dx is q a1 dx. So I'm not going to do the calculation, but it says that if I multiply y of x by a rational function, it will satisfy a differential equation. This q doesn't matter, it just comes from the calculation. But the differential equation, the a has changed to a1 to qx. That's what the consistency condition. And in general, for each n, there's going to be some an plus 1 of x, c of x, calculate it, it's not too hard, such that if I look at this, this will be a solution of dw dx equals q to the n So let's look at this equation. So I start with this equation, and I'm somehow looking at a new equation where I replace x by q. And if I start with a solution of this guy, just by multiplying by a rational function, I'll get a solution of this guy. And the point is that for n bigger than sufficiently large, the singularities that are not equal to 0 or infinity of this intersect the singularities, meaning where the denominator vanishes, a1 of x, this is going to be empty. Because the singularities here are the poles, and the poles here are just q, high enough powers of q times the pole here, and I'm just pushing them away.
You want to
Thank you. So thanks. It's nice when people pay attention. Okay. On the other hand, the solution of this guy is just some rational function times the solution of this guy. So if I had some kind of a singularity of this guy, it's going to disappear when I multiply by a rational function. So it could be at worst than that. Because whatever singularity this guy had, it's going to disappear when I look at this. So the singularities that are other than 0 in poles, other than 0 in infinity, the singularity of a solution is at worst a pole. And this requires a little effort, but you can take your solution and multiply it by a function such that you eliminate all those poles. You certainly can eliminate the poles of y by multiplying by a rational function, but you can do it in such a way that the poles disappear in the differential equation. It's a removable singularity. Again, I'm not saying how to do it, but you can do it. So, okay. So I've taken my original equation, and I've gotten this change of variables, a change of basis, so that it's a little simpler. It only has a pole at 0 to infinity. And now it's just a computation. These again will be consistent, and the only way they can be consistent is if the only non-vanishing coefficient is -1. And this really, it's just a computation. So that's what it is. But the first step is to show that the consistency condition somehow wipes out any holes that shouldn't be there. If there's anything that isn't a fixed point, can no longer really be a hole. And then looking at 0 and infinity, you just formally plug in the consistency condition. And the same proof works in general, except in first order equations, you can actually write down solutions and see what you have. For higher order equations, you have to deal with things locally. This first step is still valid, it's not hard, and it's going to be the same kind of proof. The second step, where you wipe out irrelevant stuff, you can do that locally. It's not as simple as this, it doesn't just disappear, but locally you have to make another change of coordinates. You have to do that at 0 and infinity, and then you have to take those local information and make it global. And that last step is element. So it's not exactly patching, but it requires work. And in each case, the work is separate. So in each of these various cases, the kind of thing that we do is separate. For Q difference equations, it's the easiest. So this case where you have a linear differential equation and a Q difference equation, that's very easy. And the hardest cases are when you deal with a shift or which is a Bell result. In fact, what we have written, posted on the web, contains a little gap that can be fixed, soon be fixed. It's a little side. So, well, that's the case of the proof. What else did I want to say? In the end, again, it's a formal calculation of that complex steps. There's similar results for pairs of differential and difference, when the difference is the shift, the Q dilation, and the Mahler operator, or two difference equations where you have two shifts, two Q dilation, two Mahlers, under an assumption of some kind of independence. And finally, this result has impact on some other work, and that is you can use this kind of simplification in the Galois theory. It helps in proving that certain things are coincidental, and this will be this Carlos's talk will touch on this. So that's all I have to say. We'll have 5 minutes for questions. Yes.
So, the question that you have set up with your talk is that do you prove the difference equations result, which proves the automatic sets result?
Yeah.
Do you reprove the difference equations result without using?
Yes. So this.
So this is in fact a new proof of the finite automata result.
Yeah. It through a chain of deductions, it gives you the Convex theorem.
Right.
But one, I guess it is well known that these kinds of results would imply Convex theorem. It's just a question of proving these without Convex.
Yeah.
Yes.
So you said that your proof of your main the reduction of the constant equations is analytic.
Yeah.
Are there reasons why it can't be strictly defense algebra?
Well, so
How
how can I answer that?
Well, I mean, so one way that you can answer it is by saying that there are examples of fields with two commuting automorphisms where the fixed field is algebraically closed. It's the same. So
Yeah,
it's essentially the same setup as yours, where it doesn't
Yeah,
Well, you
I don't have examples like that where you can, in fact, I'm not even sure. I'm pretty sure that by some kind of descent you can get the reduced equations and coefficients in the algebraic closure that you started with, just because it's a matrix of rational functions, and when you look at what the coefficients satisfy, it's just a system of algebraic polynomial equations. But in each of these proofs, there is some analytic continuation to get a local result like that. And I don't know how to look at that. I mean, it's a property of the proof, admit that, but it would be great to find a proof about that. And I do have to say that the analytic machine in this Reshevka, I could get to a certain point and then one really needed something serious.
The fact that you're talking about poles of a solution which a priori is transcendental means that you're using the
It was a little deceptive. I was talking about the singular points of the differential equation more than so the question about poles, when one does this in the theory, one uses formal solutions, and one uses results that's called the Turretin's theorem, which is the Jordan normal form for linear differential equations. And that's a formal result. It's not, so the local questions are almost always formal. It's just I can make these change of bases at each of the bad singular points, and then I want to do it globally all at once. Other questions? Actually, when we set up this conference, I agreed to be the chair of this session as well. So not only have I've completely taken over the session, so just live with it. Get over it, as they say.
Okay.
So that's it. Not yet?
So you're allowed to
No.
clap?
So, yeah.
Is there more questions? Okay.
Well,
You clap and then I'll make my comment. I wanted to point out that today there is coffee for sale in the, what we call the East Building. If you go down to the 3rd floor here and cross Lexington Avenue on the bridge, then right on your right there's a little stand where you can buy a fresh coffee.
All right. I have to make an apology to our speaker, Michael Singer, certainly also to Cochin, to Phyllis, and the audience, that an operator error missed the first 15 minutes of this session. No, because I pressed the shutter instead of the record, and I noticed it when the screen blanks out after 15 minutes. Sorry. So if but if you like to repeat, sometime I will re-record it. I'm sorry. I'm really sorry. It's just
Well,
happens.
it's very simple. It just means that you have to give the first 15 minutes of the talk.
Yeah, great. Well, thank you.
I'm sorry. Really,
I guess we
my
start
apologies.
again in I don't have a schedule. 10 minutes.
Oh, I shouldn't have recorded that part.